Virtual switches are software-based network switches that operate on hypervisors within virtualized environments. They facilitate communication between virtual machines, VMs, and physical networks by directing data packets to the appropriate destination based on MAC addresses, IP addresses, and port numbers. One popular example of a virtual switch is the Open vSwitch, commonly used in virtualization platforms like VMware vSphere and OpenStack. These switches offer advanced features such as VLAN tagging, quality of service, QoS policies, and network isolation to optimize network performance and security within virtualized infrastructures. Virtual switches play a crucial role in virtualized environments by enabling the creation of complex network topologies without the need for physical hardware. Through software-defined networking, SDN principles, virtual switches can be easily configured and managed to adapt to changing network requirements. For instance, businesses can dynamically adjust network policies and traffic flows by leveraging the programmability of virtual switches. Additionally, virtual switches support integration with orchestration tools like Ansible and Kubernetes, enabling automation of network provisioning tasks and ensuring consistency across virtualized environments. When it comes to implementing virtual switches, understanding their integration with physical network infrastructure is essential for seamless operation. Concepts like uplinks, which connect virtual switches to physical switches, and network overlays that encapsulate and transmit packets across virtualized networks, are critical for achieving efficient network communication. By configuring virtual switches to work in tandem with physical switches through technologies like VXLAN or GRE tunnels, organizations can extend their network reach and promote interoperability between virtual and physical network elements. A virtual security switch is an integrated software Ethernet switch equipped with security features designed to operate within virtual environments like VMware vSphere, Citrix Xen Desktop, Microsoft Hyper-V, and Virtual Iron. Its core function lies in furnishing security functions such as isolation, control, and content scrutiny among virtual machines. The inception of virtual machines in enterprise server settings gained momentum in 2005, swiftly emerging as a conventional method for companies to roll out servers and applications. To enable the deployment of these servers in virtual environments, a virtual network had to be established. Consequently, companies like VMware devised a component known as the virtual switch, meant to deliver network connectivity in the virtual setting for virtual machines and applications to communicate within the virtual network and with the physical network. Nonetheless, this virtual network architecture posed challenges concerning security due to the absence of dedicated security mechanisms accompanying the virtual switching technology. Unlike physical networks equipped with switches embedded with access control lists, firewalls, antivirus gateways, or intrusion prevention tools, the virtual network remained vulnerable. The concept of a virtual security switch amalgamates switching with security, embedding security controls within the virtual switch for per-port examination and isolation within the virtual environment. This integration paves the way for security measures to closely safeguard the endpoints without the necessity of residing on the endpoints themselves, host-based on virtual machines. By circumventing the deployment of host-based security solutions on virtual machines, a notable performance enhancement is observed during security implementation in the virtual landscape. The rationale behind this enhancement can be illustrated by envisioning 20 virtual machines operating on a dual CPU server, each hosting its individual host-based firewall. Such an arrangement would amount to 20 firewalls utilizing the same resources allocated to the 20 virtual machines, contradicting the fundamental principle of virtualization, which is to allocate resources to virtual servers rather than security applications. Centralized deployment of security mechanisms within the virtual environment facilitates significant performance gains, represented by one firewall managing security across multiple virtual machines, as opposed to individual firewalls for each virtual machine. Not limited to virtual security switches alone, switches being Layer 2 devices forming a single broadcast domain inherently fall short in replicating network segmentation and isolation, akin to multi-tiered physical networks. In response to this constraint, several networking, security, and virtualization vendors have introduced virtual firewalls, routers, and other network devices to bolster security and network organization capabilities within virtual networks. The mobility of virtual machines characterized by operating systems and applications encapsulated in a single file has facilitated unprecedented freedom akin to moving, sharing, and exchanging servers like MP3 files on peer-to-peer networks. The shift towards downloading pre-installed virtual servers from the Internet expedites server deployment by obviating the need for laborious software installation processes, courtesy of pre-installed operating systems and applications encapsulated in virtual appliances. Nevertheless, the mobility of server images poses the risk of servers being infected and circulated inadvertently. The potential scenario of downloading a virtual server infected with malware underscores the critical importance of trust consideration in downloading virtual server images. The virtual security switch concept acts as a guardian of trust decisions by furnishing isolation and security oversight among virtual machines, curtailing unauthorized communication, and monitoring malicious content dissemination or denial of service attacks. In the annals of history, Reflex Security introduced the industry's first 10 gigabit network security switch, boasting a port density supporting connectivity for 80 physical servers. Subsequently, in 2008, Viata commenced shipping an open-source network operating system tailored to deliver Layer 3 services encompassing routing, firewall, network address translation, NAT, dynamic host configuration, and virtual private network, VPN, functionalities within and between hypervisors. Over time, industry players like VMware, Cisco, Juniper, and others have rolled out virtual networking security products, blending Layer 2 and Layer 3 switching and routing capabilities.